Hello everyone, and welcome to my talk about dynamic load balancing in OpenMP. My name is Florina Ciorba. I'm with the University of Basel, Switzerland, and I would like to tell you what we have been doing to balance loops in OpenMP. Uh, we need to balance loops because there is load imbalance in certain applications that use OpenMP for parallelization, and scheduling is one way to solve the load imbalance problem. And we have been using dynamic loop self-scheduling, which is a class of scheduling algorithms that I'll describe in a moment, to do that in the GNU OpenMP runtime library implementation, as well as in the LLVM runtime library implementation. And I'll also share a few takeaway messages. I would like to first give acknowledgements to a lot of my collaborators. This is mainly funded by the Swiss National Science Foundations through a project in multi-level scheduling. We have been working with my team at the University of Basel. We have also been working, excuse me. Give me just a second. Yeah, everything is fine. We have been working also with collaborators at the University of Darmstadt, Dresden, Mississippi, OpenMP, ARB, Brookhaven, Argonne, and also with the ECP computing, exascale computing project. So load imbalance appears in computationally intensive loops that are parallelized with OpenMP. And these loops are representative of applications that are large, data parallel, and irregular in their implementation. And many applications actually spend most of their time executing loops in science, engineering, and industry. And we also have a complement from the hardware side that is also growing in complexity. We have a highly heterogeneous architecture ecosystem these days, which also leads to a large and massive parallelism that we need to exploit. And if we look at the trends, about 18 years ago, we had about 1 core in all the systems in the top 500 list, and that has grown to almost 3 digits in the top 500 list of last year. So the question is, how does the increased software parallelism execute on large parallel and widely distributed machines? Load imbalance is actually how they do it. So they execute very nicely for some parts of the application, but when there is a computational intensive loop, we can see here that there is load imbalance in the OpenMP level, load imbalance in the MPI level, and we are trying to solve exactly this problem. So the focus of this talk is concentrated on addressing load imbalance in OpenMP, but the same methods can be applied at MPI level as well. So I think I will maybe go a little bit faster over this slide about OpenMP loop scheduling. We have work to be shared among the threads that are created using OpenMP, and we can use different scheduling options to give work to those threads. If we use a static scheduling option with a certain chunk size, we may have one thread and another thread that executes with some offset in time. However, can we use other schedules that minimize that particular offset in time, which is called load imbalance? So there are some options already in OpenMP that we can use to minimize load imbalance, such as static, dynamic, guided, and auto. Auto is actually not an implementation of a particular scheduler, but defers the choice of it to the runtime system. What is important to know is that these methods have been proposed over the years, and dynamic, actually, it's called self-scheduling, which has been, it's an optimal version of list self-scheduling proposed by Richard Graham already in 1966. And guided is actually a method that has been proposed already in 1987 by Cook and Polychronopoulos, and it has been one of the first self-scheduling methods implemented in OpenMP, which came out in 1997. So are these schedules good enough to exploit the parallelism that we have these days or beyond this year? Are these schedules sufficient to cover all the characteristics of the systems and the applications? Are there better schedules not in OpenMP? And I think you already can guess the answer that yes, there are much more schedules that we should be able to use in OpenMP to address load imbalance. And I'll give you an example that we recently published in a paper that will come out early next year, where for the same example that we have shown before that comes from astrophysics actually, and this is just one iteration that is repeated over hundreds and thousands of times, The load imbalance at the OpenMP level has been almost eliminated using one of the techniques that appeared in 1990 called factoring. And we used, again, the same self-scheduling techniques at the MPI level to minimize the white space, the load imbalance at the MPI level. So yes, the answer is that there are many other options. I will maybe skip a little bit about this slide. I think we all know what causes load imbalance. Computational intensive loops are irregular, and that leads to variation in iteration execution times. System-induced variability is what I would like to focus this slide on. That comes from the differences in hardware, which leads to processing elements variability in the delivered computing speed, non-uniform memory access, operating system jitters, and other resource sharing, such as memory buses and networks if we're in the distributed memory domain. And of course, there are other delays that we cannot avoid. But what I would like to point out here is that the impact of system-induced variability on load imbalance is often neglected by the scheduling algorithms in OpenMP right now, but not neglected by the other available scheduling methods. I mentioned self-scheduling as being the central element of today's talk and all the methods that we are going to present. It's an approximation that is twice as worse as the most optimal possible schedule using preemption for a set of tasks executing on a set of resources. And the important benefit is that you don't need to worry about poor processor utilization. So it's actually perfect for minimizing load imbalance because processes or threads acquire the next computational step or the next task whenever they are ready. That leads to perfect load balance. And this is actually already implemented as dynamic one in OpenMP. So I told you that there are many more options available, and this is just a selection. This is not exhaustive. They're all based on list scheduling, starting with the 1966 method by Graham and going to self-scheduling in 86. 1997, guided was proposed. And factoring is the method that I've shown in a previous slide that was used to optimize load imbalance at the OpenMP level. And then we have another method that also combines this with data locality using fractiles. That's why it's called fractiling, factoring and tiling together. And then we have other methods that are actually adapting the allocation of work, the self-scheduling of work at execution called adaptive factoring. So there's a lot that has not yet been included in the OpenMP runtimes, in the standards, and the choice of scheduling can actually help in different situations. So this is what we are trying to explore, but the scheduling algorithm is not useful if it's not implemented in the runtime library or in a library or in a compiler. So there has been a lot of effort in implementing this in many compilers over the years, starting with 1987, and our most recent work is already in the last couple of years. I would like to focus here only the attention to some methods that have been implemented in 1998 that are not currently active today. We have started this work as an extension of a GNU runtime library implementation of OpenMP that was proposed by Pena et al. We have extended it and we have added a few self-scheduling algorithms already in 2017, and we have published different papers in 2018 and in 2019. We have a poster also, which you can see later this evening in the session, where you can learn more about that. So I would like to tell you how we have done this. So we have actually augmented the runtime. We have the challenge was to offer the user a way to choose among all the other available options out there. And for that, we could not extend the standard because then we would have an endless list of schedule clauses to explore. So the idea was to use the runtime to extend the runtime so we don't modify the compiler, and to defer the scheduling choice to execution time by setting the environment variable to one of the newly added methods. And in the code, we only specify that the schedule will be defined at runtime. And this is useful for the OpenMP runtime implementations used by Intel, LLVM, and GNU. Okay, so we have some results already published a year ago at IWAMP in Barcelona, in which we have added factoring 2 as a practical implementation of the factoring method. Trapezoid, weighted factoring, and random. Random is a method that we used only for baseline comparison. What is important to know is that when we when we define new schedules, that was the design strategies for the schedules that have been proposed here, is that they want to minimize the scheduling overhead of allocating work at runtime, and also minimize load imbalance. So the ideal point would be here. Self-scheduling is here where there is no load imbalance, but there is overhead because you only give one single work item at a time. Static is actually on the other extreme where you have no scheduling overhead because you can pre-compute the amount of work that can be taken at runtime by any available thread, and load imbalance, however, is not guaranteed. So there's a sweet spot between between these extremes, and there's also a third dimension of locality, right? So we don't only care about load imbalance, we don't only care about scheduling overhead, we want to also minimize locality, and there's one method that I already mentioned that does that. The other ones don't take into account, but that's future work for us to implement in the runtime. So we have been, as I mentioned, we use this through the runtime and through the OpenMP scheduling environment variable. It is important to note that even though we've done 2 implementations, these mechanisms, the scheduling mechanisms, are not limited to a single runtime implementation. So they can be used in any runtime library that implements OpenMP. Okay, we have some experiments that we have performed on a 2-socket machine with the field pinning, with a pinning where we had some oversubscription of some nodes, more oversubscription, even more oversubscription, and so forth. So the question was, does a schedule benefit a parallel loop, and can it handle hardware heterogeneity as mimicked by this oversubscription of a single socket? So for our experiments, we used 20 threads, as we have seen. We compared against the existing implementations in the standard and the newly added scheduling algorithms. 5 pinnings, these are the hardware descriptions, and we also repeated every experiment 20 times to take the average of that. The median, excuse me. So we see for an adjoint convolution, which is a computational kernel, is not a full-fledged application, which is actually triangular, so it has more work at the beginning and less work at the end. That's why it exhibits load imbalance when implemented using an OpenMP work-sharing loop. For a 10 to the power of 6 number of iterations, and the variation between the execution of these, every of those iterations, the variation, the statistical dispersion is actually 57%. So ideally, if every iteration would take the same amount of time, the variation would be very small, which tells you that this is highly variable, therefore it could benefit from additional methods. And we see here that static and weighted factoring are the least sensitive to pinnings. Here are the 5 pinnings for every method. So basically they offer almost comparable results. No, these are the least and these are the most sensitive to pinnings, excuse me. And here we have the best performing method, which is not one of the 3 methods that currently, the 3 methods that currently exist in the standard. So that means that there is room for improvement. And the least performing happened to be guided self-scheduling for this particular case. We have another example from the Rodinia benchmarks. It's a molecular dynamics kernel, which has much smaller number of iterations and just as high variability between the iteration execution times. And we see also the most sensitive to pinnings here due to some initial calibration to calculate the difference, the weights between the different hardware cores, because we have oversubscription. Here we have no oversubscription, and for the last 3 pinnings we have oversubscription, so we can see that they perform poorly. However, the best performing happened to be again factoring 2, which is very close to GSS and TSS and to the other method, but for a no oversubscription. And the least performing happened to be dynamic 1 or self-scheduling. So the idea here is that we have additional schedules that provide benefit over existing schedules. However, when the application is quite uniform, not irregular, and not very large, static is actually sufficient. So here's not the method that tells you that you should just discard all the methods that are already present in the OpenMP standard. But if you have a computational loop or several computational loops that are not showing the best performance, but they still show load imbalance, there are other methods out there that one can use. And they are, excuse me, the good news is that they are immediately usable. So we have this library available online. Please feel free to download it and play with it. I'm not sure how am I doing on time. I should maybe wrap up. I will have more slides available online. I will just like to summarize a little bit what we have been doing for LLVM, for which we had to change just three functions in the KMP dispatch file. We have added a few more functions, a few more scheduling algorithms, factoring. Trapezoid was actually already there implemented, but is not conforming to the standard. So we added it here. So we expanded our LLVM implementation just with factoring. We have interesting results that show, here we have the details of the experiments which you can see online, that if we wanted to analyze the overhead of calling scheduling methods through the runtime versus calling them directly through the standard compliant implementation in the compiler. And we see through the reference static, guided, and dynamic called by the standard, by the compiler, static, dynamic, scheduling, trapezoid, and factoring. Only dynamic has a little bit of overhead, which tells us that these are still useful if we call them through the runtime. Of course, they are not ideal. We could do much better, and we're working on that. And so there is some room to explore in between those two extremes. I will just show you these two results, and then I'll try to wrap up. For more details, please come see us at the poster. For one case that we have also seen in the previous paper, adjoint convolution, which had a high variability and many iterations, static performed poorly and dynamic performed the best. And because we have inherent load imbalance that dynamic actually is able to mitigate. Static isn't able to do that. However, we have a converse performance for a dynamic and static when we go to the molecular dynamics benchmarks we have seen before. So I would like to skip to the takeaway messages here. The last part of the talk was about the poster that you can see already at 5 p.m. today. We have shown that it is actually possible to do better that is currently available in the standard. The standard was never meant to cover all possible cases, so we're here to actually show that we could complement the standard in this way. And more schedule are needed, and we have two implementations already there. In fact, when you don't know, so even if we offer you all of these choices, we are going to release this library very soon, in a couple of weeks. Even if you start using that library, you won't know how to choose. So as a rule of thumb, please already use factoring too, but feel free to explore other schedules as well that may be more useful for your application and your system and your scheduling loop. And remaining questions for us are how to incorporate more runtime information to actually give more information to the adaptive scheduling techniques to eliminate load imbalance even more, and also to allow the users to develop their own scheduling techniques. And we have some already existing efforts on that. We have a publication at IWAM this year, and if you want to know how this benefits real application, not just microkernels that have a single or a very simple loop in there, we have applied this to a computational application from astrophysics, and we have seen that doing dynamic load balancing at the MPI and OpenMP level gave us an improvement per time step of up to 40%, and overall over 3,000 time steps of 15%. So there's a lot of potential to use dynamic load balancing at runtime. I think there's time maybe for one question. If not, I'm available around for further questions. Thank you for your attention. Here are the takeaways messages. Yeah.
When you say dynamic, are you using monotonic dynamic or non-monotonic dynamic? Because at least in the LLVM runtime, the overhead is very different.
Yes, we are using monotonic dynamic at this point, but we are exploring exactly this challenge, especially because load imbalance is important to be correct, low overhead, and also to maintain data locality. So yes, it's a very good point. Thank you for bringing that up. Thank you very much.